So let me share with my slides. Can everybody see the slides?
Yep.
Okay. So also the transition of slides is working properly.
I don't see the transition.
You didn't see the transition? How about now?
No, still nothing.
Oh, let me redo it. So can everybody see the slides now?
It looks like it's still waiting. It's like it's still just black. It's still just black and says that you started screen sharing. It might come up in a minute.
Okay. Okay. Yeah. While we are waiting, I just want to remind everyone the due of our homework 1 is Friday, meaning tomorrow, and I believe everyone has already started. And but if you still on halfway, please speed up.
Will the scale of future assignments be similar to the scale of this assignment?
You mean the following assignments?
Mm-hmm.
Most of the following assignments will be similar. Probably we'll have a less workload on the last assignment, I think, because I want to allocate some time for everybody to review for the final exam. But I mean, homework 3, homework 4 is like this. Some kinds are like this, but probably won't require as much coding as in this work, because in this homework you have to implement decision trees from scratch, and all those recursive algorithm. You might feel a little bit more as compared with the models we're going to discuss later, like linear regression, support back machines. Yeah, that's it.
Okay. I think for this assignment, like the part that took me the most time was doing the manual decision tree creation, just because like I would make a mistake and then have to redo a full decision tree, and it took a lot more time than I was expecting. So I wanted to give that feedback a little bit.
I'll suggest you to first, I mean, when you do this manual creation, you need to first check every step you're doing rightly before you write down the whole procedure in homework. Otherwise, like if you create it while you're typing LaTeX source code, of course, like if you found something wrong, you have to wipe out everything you have written and start from scratch. That is ineffective. So yeah, I suggest you to first do it on some paper with your pen, for example, and you calculate it, and you verify, okay, it is right, and then just write them in a LaTeX file. Does it make sense?
I mean, yeah, that does make sense. I think that a lot of manual procedures just in general take a lot more time than like writing the programs. And I don't know if it offered, at least me personally, a lot of extra understanding about the algorithm. Like doing it one time, I was like, oh yeah, I didn't realize that's how that would play out. But the assignment had us do it like 3 or 4 times. And I felt like that wasn't incredibly valuable for my learning.
Well, I think it covers all the three principles we discussed in creating the decision trees, right? The information gain, majority error, and what else?
Gini index.
The Gini index, yeah.
Mhm.
So I want everybody to practice on that. I don't think all the problems are the same. They actually have some kind of variances on that.
Yeah. So for example, right, like as you said, it covered the three of those. Um, when you covered the different, like I think this is in still part one, but like the second part of that, where it covered the different approaches to filling in missing attributes. I think that was a good structure because it only had you do essentially one layer of a decision tree for that different strategy. And so I got to go through it, right, and like see how it worked out, but I didn't have to create a whole tree by hand according to that rule, if that makes sense. I think the biggest part is that this class has had like at least with that one assignment, more than double the workload of any of my other classes. And so I'm just kind of like, I don't know if you're aware of that.
Yeah, I do aware of that. That's why I warn everybody at the beginning.
Yeah.
Not easy going class. You have to take more time on that. And also, I don't request everybody to write every detail of that. So I know many people came to me and saying, okay, is it necessary for me to write down every procedure to calculate every information gain? I said not. Just to show one time, but you need to show the steps. Like, okay, in the first step, which feature I choose? Why? Because their information gain is blah blah blah. You can just calculate. You can use calculator to do that. You can use Excel to do that. You can even write a program to do that. And what you need is just list the steps.
Yeah, I definitely think there's obviously some space for like figuring out what exactly you expect and trying to reduce, any possibility of having to redo work and all that. But yeah, I don't know if any other students have also felt that the assignments in this class have been pretty large, but that's how I feel.
Yeah, thanks for reminding this, but I have here everybody the message. This class is not a light class. It's you have to do work to fully understand the algorithm. It's not like, okay, I show you the pseudocode and looks everybody on the same page and you can follow every step. Yeah, that's just understanding the paper. You have to do both manually and programming debugging on that. That's how it works. But regarding the workload, like for example, if you don't want to, for example, you want to avoid tedious steps, for example, if you feel it's too simple, like you feel like it's just meaningless repetition, that's fine. An easier way is that, okay, now that you have implemented the code by itself, you can run your code and just use the data on the problem. I can just write the steps. I just copy the steps print out by algorithm. That's allowed. That's allowed as well.
Mm-hmm. Yeah. I guess yeah. If
But the workload is there. don't bargain with the workload. It's not. It won't be changed.
All right.
But if you do feel like this is kind of tedious, like we can definitely discuss like how to reduce the workload on writing. Like I really don't want everybody to read every line of steps. How do you calculate information in every step? It's not necessary. It's definitely not necessary. But I do want everybody to list the steps, the algorithm steps when you apply it. That's the most important thing.
Then how about, I guess, like if I find that work is redundant or like unnecessary and I'm not learning from it, I'll like before doing it, I guess, in the assignment, if I just like, write you a message in Canvas or something like that, and in that sense, would you take that feedback, or would that be not very useful to you?
Yeah, you can give me feedback. Probably I can consider adjusting that, but if the homework is out, then you have to do that, right? You can't say, okay, professor, I don't like this problem because I feel it's redundant, it's too easy to me, so I refuse to do that. Well, this is not.
Yeah, I mean that's partially why I waited until now to talk about it, because I've already completed the assignment, and so it's it's done and gone, right? But
yeah, I'm happy to hear that. Yeah.
But I wanted to let you know that like there were definitely a few moments in the first part of the assignment at least where I was like, yeah, this is kind of pointless, and I feel like I've learned it, and some of this is redundant.
So probably you're doing excellent for this job. So you're feeling that okay, this problem is useless or pointless for you because you practice once, everything is kind of like very natural. It's not unnecessary to practice again, but it really doesn't necessarily work for everybody.
Of course, yeah. I mean that
the homework is not designed for only for you, right? It's designed for a whole like 50 students or more, or 60 students. I actually don't know the actual number of students to register this class.
Yeah, I can only speak to my personal experience, right? Like I can't give reviews for other people. But
if everybody say, okay, this is too simple, this is really useless, and we without that we can do perfect job in implementing my decision trees. Yeah, I can definitely consider for that. Definitely.
All right, thank you for your time. I think we can probably.
Yeah, we can discuss offline. I mean, if you have some other opinions about this homework assignment, but as I mentioned at the very beginning, the workload is really heavy. It's not joking, and if you decide to do that, please take your time. I mean, if students are very smart, feel like okay, this is our minutes, that doesn't necessarily mean you can cancel those problems. You can consider a way to reduce the work amount by like writing less. That's fine. Well, we can definitely discuss about that. But you can also say, okay, this is useless and this is pointless. I already know everything. I don't want to work out these simple problems. Then how do I evaluate your homework, right? If you don't do homework 2 and 3 and everybody else has done that, how can I give you a grade, right? Okay. Any other question regarding the homework? Oh, great. So anyone who is still working on that, please hurry and work on that. And hopefully we can collect all the submissions by end of Friday, because the homework 2 will come out very soon. I don't want like you're struggling with 2 homeworks simultaneously. Okay, so can everybody see the slides right now?
Yes.
Okay, great. Takes a while, right? So the transition is okay as well, right?
Yeah.
Okay, great. So let's just spend a few minutes reviewing what we have discussed in last lecture. So we talk about new type of machine learning methods. It's called ensemble learning, right? So basically, ensemble learning assumes that we have some base learner, which can automatically generate some hypotheses given the training set, right? So ensemble learning talks about how to combine a set of hypotheses generated by the base learners and to make it much stronger learner. So two types of ensemble learning is kind of dominant, very widely used. It's called one is called boosting, the other called bagging. Bagging is our focus today, right? So in the last lecture, we mainly talked about ADA boost, the most successful boosting algorithm. So what is ADA boost? Sorry. So basically, ADA boosting as well as other boosting algorithms trying to adjust the weights for the training examples. So in each iteration, and they're gonna learn a weight hypothesis based upon the current weighted training examples. And then according to the prediction error, meaning on the training data, meaning the training error, they're gonna reweight the weights of the training examples and then proceed to the next round. So, and after like running a pre-specified number of iterations with big T, and we can stop and we collected like big T number of weight hypotheses to combine them through a linear combination. So the algorithmic details is as follows. So initially, we set the weights for all the training examples to be the same. Right? So suppose we have m training examples, so the weight for each example is just one over m. So equivalently, will all the training examples are equivalently important, right? And then by going through each iteration, we first find a weight classifier whose weighted classification error is better than chance, meaning that less than 0.5, right? And then we compute its vote, meaning when we finally integrate them together to get our final hypothesis, how important the prediction made by this hypothesis is. So alpha t is computed by 1/2 logarithm of 1 minus epsilon t over epsilon t. So epsilon t is a weighted error. So because epsilon t is always less than half, right? So this fraction is always bigger than 1, meaning that also alpha t is positive. And then we use this alpha t. We're going to use this alpha t to update the values of the weights for the training examples. So how do we do that? If our prediction is correct, meaning that the product between the ground truth label yi and the prediction is positive. Remember, we have discussed that there's a smart condition, like test condition. If your prediction is correct, then this product is always 1, right? If it is wrong, it's always -1. So if your prediction is correct, you're actually multiplying the previous weight by a scalar e to the power of minus alpha t. So this value is less than 1. Of course, it's bigger than 0, meaning that you're downweight this training example because it has already been correctly predicted. However, if you make a wrong prediction, this product becomes -1. So minus becomes positive. So you are multiplying this sample weight by a scalar which is bigger than 1, meaning that you are promoting the importance of this example because it was misclassified by the current hypothesis. And finally, we're going to normalize all those adjusted weights to ensure the summation is 1. With those new weights, we proceed to the next round of learning or iteration, and we train our weak learner again to get a new classifier to be denoted as HT+1, right? So in HT+1, it will focus more on those misclassified examples in the previous iteration. Hopefully, the new classifier can correct mistakes made by the previous hypothesis. So do this again and again until all the big T iterations have been finished, and then we just combine them and weight each prediction by the alpha T. So if you're doing like binary classification, finally you just look at, okay, how many votes the positive prediction can get, and how many votes the negative prediction can get. And if positive votes are bigger than negative votes, so this summation should be positive, and the sign will be positive as our final prediction. Otherwise, this summation will be negative, sign is -1, will be used as our final prediction. Okay? And from the toy example we have discussed, right? So we say that these 3 weak hypotheses, they have very simple classification boundary, like 2 vertical lines, the 1 horizontal lines, alpha 1, alpha 2, and alpha 3, right? But if you just combine them together, you see that actually the classification boundaries are much more complex, right? So they are strong enough or expressive enough to separate every positive examples from the negative examples. We have also showing that some theoretical guarantee about training error. So naturally, intuitively, we think that, okay, if we just run more and more runs, like more and more iterations, our training error can go down to 0. Right? So actually, this is guaranteed by this theorem. So the training error can be upper bounded by e to the power to the power of -2 gamma squared and the big T. So gamma is kind of lower bound in all of this gamma T here. But anyway, this just shows that, okay, when you train more and more iterations, the training error actually goes down exponentially. So this is a typically training error curve along with more iterations. You can see how fast it goes down to 0, and this is a typical behavior about the performance of individual classifiers. We have discussed last lecture, right? Because in the later stages, those classifiers have to deal with those hard to classify examples because only their weights are kind of kept being amplified, right? So, but a very interesting property observed in boosting type algorithms that they are much less sensitive to the overfitting issue. So in our previous discussion, we showcased that the learning curve for decision trees, right? And when we keep growing the tree, right, the training error keeps going down, but at some time point, the test error becomes going up, showing that, okay, those expressive classifiers, the models are easily affected by noises in the training data, right? At some point, if you keep feeding the training noises, the test error is increasing, meaning that the generalization performance is going to be bad. Right? But this phenomenon is not very obvious for boosting algorithms, like data boosting. So from this figure, you can see that, so the blue line shows the training error, and red line shows the test error along with the number of iterations. You can see that even when the training error goes down to 0, the test error does not increase. Instead, it is either stable or even slightly going down. So this is kind of an open question, and several possible explanations have been provided. So what we can conclude is that, okay, compared with other complex machine learning models like deep neural nets or whatever kernel methods, boosting type of methods are really kind of more robust to overfitting issue. Okay, that's what is a brief overview of ADA boost. Any question regarding boosting and ADA boost?
Yeah, I have a question, and I'm sure you're going to get to this probably eventually, but I guess I just have a hard time understanding like what, because you said that decision stumps are commonly used as your weak classifiers.
Yep.
But then when you kind of showed it visually, like in this example, H1 and H2 and H3 were very visual. They were just like horizontal lines that are splitting the data. But it kind of seems like if you use like a decision stump, that gets harder to visualize like this. And so like, I guess I'm just curious, like, are we gonna talk about like a more specific example of how that's used? Just because I just have a hard time understanding how this generalizes, I guess.
Assuming you feel this horizontal
This
line.
makes sense. This makes sense. But then like putting this in context of like face recognition, then it's like harder for me to see how like this really like translates to a more specific example, I guess.
Oh yeah, yeah. That's a good point. So actually, if you want to apply to more complicated applications, I guess you're referring to this, right? So this example is totally pedagogical. It's for teaching. It's not for practical usage.
Right.
It's just leave a high level idea. But if you want to see more complicated application, I can provide you more references, but it's not appropriate to talk about in class because
Sure.
yeah,
Okay.
we will apply to face recognition, right? So a very important step is how do you construct the features out of these images.
Right.
The image is very, very like high dimensional feature vector, right? So you're gonna first extract a bunch of features and feed them to Ada Boost.
Sure. I guess like if we're maybe I'll just hold on. It sounds like you'll be giving us the information necessary layer by layer. So I think we're good.
Yeah. We don't have time like to go through some like for example for image processing. Actually, one very important step is to extract features like HOJ, like
Right.
gradient, whatever. So there's a bunch of features on that. So the most popular Ada Boost is based on a few like elaborated very effective features. You have to do that first, and then you run pretty exact or similar algorithm framework to train your Ada Boost. And also you need to reformulate the problem, like you have to calculate bounding box, right?
Yeah.
And then you need to know, okay, how large is the bounding box? So there involves a lot of like pre-processing and post-processing procedures. It is not very intuitive to show them on the slide.
Yeah, okay. I definitely see what you mean. Okay, thank you.
Yeah, if you want to know more about that, we can discuss offline. Actually,
Sure.
The classification of objects and detection of their positions is kind of you have a lot of other problems you have to solve. It's not only you just train one machine learning algorithm and
Okay.
it's not like that.
Cool.
Any other questions regarding the Ada Boost and boosting type of algorithm? Okay, great. Because in our next homework, everybody will be requested to implement your own Ada boosting based upon your implementation of decision tree. That's why, I mean, the a correct implementation of decision tree is really important because it will not only be used for homework 1, but also be used for homework 2. Okay, so today we're gonna talk about another type of ensemble learning approach. It's called bagging. And also, of course, we're going to focus on the most popular bagging methods called random forest. So again, bagging methods is also a kind of meta algorithms that combine the output of multiple classifiers. We assume that, okay, you have some learning algorithm which can generate classifiers according to different training sets. And bagging as other ensemble learning, just consider how to combine them. And bagging often tends to be empirically robust. And an example is that in the 1 million Netflix prize in 2009, the winner actually implements a giant ensemble. So let us first talk about the general framework for bagging. You see that it's kind of straightforward, but you see actually even although it is simple, but it is really working. So assume that we still have an M training example set. It's the same setting as the boosting. And we also run big T iterations. But other than different from the Ada boosting where we're gonna reweight the training examples, right? Bagging doesn't weight training examples at all. Instead, in each iteration, bagging will sample a new set, a new data set, based upon which to learn a classifier. So how do we sample a new set? We use the so-called uniformly with replacement. So we will the original training set as kind of data source. Then we just randomly draw samples from this data source uniformly with replacement. I suppose we draw M prime samples. So M prime is really less than or equal to M. And after we have collected those M5 examples, and then we train a classifier. We can use any classifier to train, like CT. We can denote it by CT. Right? So obviously, different iterations, you can get different varying training set, and finally you end up with T different classifiers. And after we finished all the big T iterations, we construct the final classifier by taking the votes. It's the same as the eta boost, but we don't have any like alpha t's values as the weights. We just will every classifiers as equally important. Right? We just look at, okay, how many positive predictions come out from those T classifiers, from how many negative predictions come out from this big T classifiers, and then say which class finally got the largest vote, and then will be used as our final prediction. So any question regarding this general framework? So it looks simple, right? Okay, great. So now I want to particularly emphasize how we draw these new samples uniformly with replacement. But I guess most people are most of you are familiar with this, right? This is just some terms from statistical class. So just in case, right? We need to be aware that because we're sample from the original training set uniformly with replacement, it implies that in our new training set, there can be some duplications because this is with replacement. Like when we sample one sample and we place them back, and next time we sample it again, it can show up as well. It can show up again. Right?
So the M prime, the subsets, right? I see there's a repetition of X1 in the first example.
Yes.
Isn't that just like wasted space though? Because the most classifiers won't like, or at least the decision tree classifier won't, it won't really be able to use two of the exact same examples.
Oh yeah, you're right. This is just to conceptually show the bootstrap sample. But in your implementation, I mean, you really do not necessarily, keep two identical samples. Right? You can just keep a count for them.
Keep a count, like to weight it?
You can say it's weight, but it's just count. Like, say I can have 5 examples, but I know X1, it has a duplication count to be 2, right? X2, duplication count of 2, X4, duplication count as 1. I mean, this is regarding how you implement it.
Mm-hmm.
But
is there a reason we would want this? We would desire this behavior? Like, I could definitely see why you'd want, you'd want, say, X1 to end up in different bootstrap samples, right? Duplicates of X1 in different bootstrap samples. Mm-hmm. But I don't know why you would want duplicates of X1 in a single bootstrap sample,
You mean you'll feel more satisfactory that this M prime samples are unique?
No. So like the M primes can be overlapping, but I don't know why you would want the M primes to have duplicates within themselves. I don't see the value in that, and I'm kind of wondering if there's something I'm missing.
Oh, okay. To explain that, let us use a little bit statistics. Okay. So this technique is called bootstrap. So if we set M prime equals to M, I want to sample exactly the same number of training examples, but just uniformly with replacement from the training set. Why we do this, right? That's your question. So the justification is as follows. So they want to construct a new data set for every iteration, meaning that I want to draw a new data from the data distribution every time. So that based on a new data set in each iteration, I can train a new classifier. That's the idea. But the problem is that I cannot do this. I can only assume I can access the original training set. But then how can we construct an approximation to the data distribution? We can use the training set to construct such a distribution. So this distribution, if you write it down, is actually an empirical distribution. And now I can view the empirical distribution constructed based upon the original set as our data distribution. Now I just use data distribution to draw like apply examples for each iteration. That's why it is uniform with replacement. Uniformly sample with replacement is equivalent to sample a data distribution, an empirical data distribution constructed from the training set.
Okay, so it's to match with like a mathematical definition of, you said the empirical distribution?
Yes. So empirical distribution is it's just like a multinomial distribution. Like you have suppose you have m examples, right? So I have m examples, you have a uniform distribution to sample each data point. That's it. We have some theoretical guarantee like that when along with more and more examples, your empirical distribution will converge to the true distribution, no matter how your true data distribution look like. It always converges to that.
Gotcha.
So the idea is that, okay, I cannot access the true data distribution. So I'm gonna use the current training set, the whole training set, to construct a surrogate.
I see. So if you do it without replacement, then you're all of a sudden kind of imposing a limit on it that that would break that that theoretical guarantee that you'll approach the distribution, right?
Yes. Yes.
Okay, that makes a lot.
It's hard to show anything because you always need to, according to law of large numbers, you have to show some convergence. Then you need to ensure that, okay, every data set in this data distribution will finally converge to the true data distribution if we increase the number of samples.
Okay. All right. Awesome. Thank you.
Any other question? I mean, regarding, if you feel uncomfortable with that, but just just want to give you, yeah, they're justified. They're theoretically justified. It's not like, okay, I intentionally want to do it with replacement, because this is doing some sampling from the surrogate distribution to the true data distribution. Okay, so let's go back to the algorithmic detail. Right? So I just want to I show this piece of examples just to remind you that, okay, there can be some duplications, but it's not necessary to be duplicated as in a way I show the examples. Right? So suppose we only have like 5 examples, like x1 to x5. So our m equals to 5, and our m prime equals to 5. So when m prime is same as m, this sampling technique is called bootstrap. And it relates to many classical statistical estimations like jackknife. If you have taken a statistics class, they should introduce such kind of like jackknife, such kind of statistics. This is working effectively for when your data sample is small. But anyway, we can say, okay, in the first bootstrap sample, like our first sample is uniform drawing from this data set, right? My x1. But remember, this is with replacement, meaning that we do not, once we sample x1, we do not kick it out. We still put it in the back. And then we sample again, okay, x1 bingo, we're selected again, so it's plugging. So it shows up the duplication here, right? And x2, same one here, x4. And similarly for once you draw n primes times, you collect one subset of training data, and it's not subset. It's just one set of training data for this particular iteration, and based upon that, we're gonna train a classifier with say decision tree. So now you can see that the training set has some duplicated examples in for decision tree construction, but everybody should be should won't feel uncomfortable because we know how to deal with duplicate concept. Remember, we talked about the fraction concept. That means if I have some fraction or if I have some any scalar multiplying with this example, we know how to deal with it.
Are you saying that we should use fractional weights of 1/2, say, for this duplicate?
It's not 1/2. I'm sorry. It's kind of confusing. I'm not saying you're using 1/2. You are using the weights for the examples. Like you have so here the weights for this particular set, right? So you actually have 3 unique examples, right? But for x1 you have a weight 2, x2 you have weight 2, x4 have weight 1, right? So when you train a decision tree on that, you have to take into account the weight of those examples in the tree construction, just like the way you deal with fractional examples. Is it reasonable? Any question? Okay, so assume everybody won't be unsatisfactory with these duplicated examples, but everyone should be aware that, okay, by using this bootstrapping tactic, you might have to face duplicated examples. Oh, by the way, I didn't see the chat. I didn't see the chat room. So if you have any question you want to ask, just you can just say it. A second, let me pop up the chat room. I see you. Okay, so let us continue. So can everybody see the slides correctly?
Yeah.
Okay, great. Yeah, so this is just the whole framework. Like we actually, according to this, using this framework, you can implement any bagging. Bagging with any classifiers. So a short summary. So bagging is a method to generate multiple versions of predictor and using this to get aggregate predictor. So if we're doing regression, we just average the prediction, the continuous prediction by each predictor. If you're doing class classification, like say if they're doing like 3 class classification, like we just look at how many votes class 1 has got from all those predictors and how many votes class 2 got, how many votes class 3 got, and then you just take the one who has the largest vote as the final prediction. And the multiple versions are constructed not by, the way in the Bootstrap does, like we wait in examples. Instead, we're making bootstrap replicates of the learning set and use this new training set to train the classifier. And in many real-world and simulation testing, it shows that bagging can substantially improve the accuracy, especially if your predictive model are kind of sensitive to the change of training set. For example, if you just slightly change the features of several training examples, or you just alter the labels for training examples, I mean, not many, then the model, the learned classifier, can change a lot, and the bagging is particularly useful for those type of classifiers. And most commonly used base learners for bagging, again, is decision trees. If you want to learn a baggy decision trees, you just draw two bootstrap sample sets of the original data, and for each training set, bootstrap training set, we train a tree. Right? Then we collect a set of T trees, and then we average the prediction of the trees on all of back samples. So here just visualization of this procedure, but those trees should have different structures. So we'll focus most on the baggy decision trees, and in homework 3, everybody will be requested to implement your own baggy decision trees. So that means we want to look at the details in the pseudocode so that everybody can follow it comfortably follow it. So given a set of training, given a training set with M examples, we'll repeat like big T steps. So by the way, bagging is kind of like can done in parallel, meaning that we do not need to like sequentially perform each step. Instead, we can do it in parallel. So in each iteration, we draw M examples uniformly with replacement from the training set. And we denote the training set by XD and YT. Right? And then we can learn decision tree CT from XD/YT using ID3 algorithm we have discussed in detail previously, right? Or card algorithm or even others. But we do not need to prune our tree or limit the depth and width. That means, okay, we can just safely grow the tree until it stops growing. It's not necessary for us to control the growth of the tree. And then when we collect all these big trees and in the final prediction step, we vote or average T predictions for classification or regression respectively. So now I want to ask, now that we do not require the pruning of the tree or controlling the growth of the tree, what kind of classifier do we have in each iteration? How is it different from AdaBoost? Any thoughts?
So in AdaBoost, we run the algorithm on full data, but here we are running on kind of subsets of data. That's the difference, I think. Like we design trees in AdaBoost on the whole data, which actually according to uh, according to the weak classifier. Let's say if it is a decision tree, it will still have access to the whole data. Here, the smaller decision trees might not have access to the whole data. They might only have access to a subset of data.
Yeah, I think you covered what you covered is great, right? It's great. So firstly, yeah, we use bootstrap sample to retrain our data, meaning that okay, is we train our classifier on this kind of similar subset of data, but we should still be aware that even use uniformly with replacement, we still have a chance to sample the full data, right? But the chance is quite low. The chance is quite low.
Yeah.
Yeah, but the second point I mentioned is actually the most important. Actually, in the classification learning, in the classifier learning step, we are not seeking for a weak classifier, Instead, we're trying to learn a strong classifier. So this is a key difference from the boosting or ADA boost algorithm. So remember the ADA boost we discussed before, right? So you have to ensure your hypothesis or classifier is weak enough. It cannot be too weak. It cannot be too strong. So that's why in the last lecture we suggested to use one level decision stump to do that, right? But for bagging, there's not any constraint. You don't, actually, we do not want you to use weak classifiers. We want you to use strong classifiers, even if overfit the train data. That's fine. We can just let your tree to grow anywhere. And finally, we just collect those big T number of large trees together to average their prediction to give our final prediction. So someone will ask why it works, why we have a set of, we just average a set of like large trees together, it can improve performance. So here we'll give some like theoretical justification. I want to express some insight behind that. So it's called bias plus variance decomposition. It's very famous, very well-known analysis in the development of machine learning theory. But intuitively, once we average things together, right, we can expect we got more reliable, more robust estimation. This is consistent with our practice, right? So in whatever applications, if you want to measure some random things, right, you take multiple measures together, you do the average. In that way, you can reduce noises, you can improve confidence, whatever. There are numerous justifications in statistics to show that, right? And here, I want to show why we use bagging to learn a bunch of like big trees together. When we do the average, we can also improve the predictive performance. And we're gonna illustrate by looking at a particular new test example, X star. So again, we assume we have collected a training data set by denoted by D. We have a learn predictor by H. H is actually run our learning algorithm on the training set D. So H is not only determined by the training algorithm, is also determined by the training data set D. Of course, different training data sets will give you a different learn predictor. And also we assume we have some underlying target function f, right? So all the true labels are given by evaluating f at the inputs. And now suppose we're given a new test example x star, which are fixed and constant. We'll only look at the prediction performance at x star. But of course, this conclusion later we'll see can generalize to arbitrary new test examples. So now we want to analyze the square error average over all possible training data. So basically, we want to calculate this. We want to calculate this fx star subtracted by h of x star and take square. So basically, it means okay, the square difference between the ground truth prediction and the prediction made by the learner. And as we just discussed, different training set will give different learner, and in turn gives a different prediction. So we want to calculate expectation. So when you take the expectation over the data distribution, this performance reveals how good your training algorithm is, right? Any question regarding the setting so far?
Yeah, I have a quick question. So are you just saying that essentially by using this bagging method, it helps reduce the chances of overfitting in just using a decision tree by itself?
Well, I'm not saying it's reduce the chances of overfitting. It still overfits.
Okay. I guess like I'm just trying.
Yeah. What I'm trying to say, okay, even it overfits the trained data, but you show that by average them together, you still get a good performance in the generalization.
Right. I guess so. I guess I'm just having a hard time seeing like, so I guess maybe why would you want to use bagging over just using a decision tree?
Yes.
A single.
Yes, that's the point I want to explain.
But I guess why is it the case?
Why is the case?
Yeah.
Why you mean why using bagging of trees will outperform using single tree?
Yeah, that's just I'm still a little bit confused on how that's the case.
Yeah. That's right now we're discussing. I'm going to show that why
Okay.
will outperform a single tree.
Okay. Sounds good.
So how do I show that? I just want to analyze this square error, because this square error actually measures how good we predict a particular training example, right? A test example. Okay, so now let us look at this expectation of square error and see what kind of structure can we find, right? So we're gonna use a kind of a classical trick in statistics. So inside this parentheses, inside this exactly bracket, right? So I'm gonna subtract by we're gonna subtract this ground truth prediction by this expectation of the prediction of a learned hypothesis plus the expectation of the learned hypothesis. Okay. So you can see we subtract this term by one extra term and adds it back, so nothing changed, right? So it doesn't change the whole value. And this expectation is actually the average prediction of your learned hypothesis over all kinds of training sets. And now I want to expand this square terms. So this quadratic terms actually have three terms, right? The first term will be the square of this difference, right? Fx star subtracted by the expectation of the learned hypothesis prediction and take square, right? Take square, and then outside you take the expectation over data distribution. And the second term will be the square of this term. The square of the expectation of the learned hypothesis prediction subtracted by learned hypothesis prediction, and outside you take the expectation again. And the third term will be the cross term. So this term and those terms, you just do the cross product, right? Cross product, and this guy multiplying with this guy, and of course you need to multiply scalar 2, and outside you take expectation, because expectation is here. This is just the trick we have used many times to expand a quadratic term. So now, what about the value of this term? What about the value of this cross product? Did anyone give me a hint? What is the actual value of this? Any idea? Any thoughts? Yeah, we can take a closer look, right? So, so first of all, those ground truth prediction, right? Because X star, the test example is fixed, right? So the predictions here doesn't have any randomness. So the expectation, the expectation is itself. And second thing is about this term. Right? This term is the expectation over the prediction made by the learned hypothesis, right? Because it has already taken expectation. Right? it has already been a constant. I mean, meaning that, okay, this term, this difference term, right? We can move out. We can move out of this outer expectation because they're constant to the data distribution D. So the remaining thing will be like expectation over this guy. So again, because in the first term, the expectation has already been taken. So it is constant. Right? Then what you need to do is just move the expectation of D with respect to over this one. So now what we can see. We can see that actually if you take expectation over this, it simply becomes 0, right? Any questions so far? Okay, so I hope, assume everybody is comfortable with this. So it's simply 0, right? So if you still not see it, we can just grab a paper and copy and write down those equations. You'll see that it's simply 0. And now we only have 2 terms left, right? This expectation of the expectation of 2 square terms, right? So the first term is expectation of a difference between the ground truth prediction and the expected prediction made by our learned hypothesis. Here, the expected meaning that, okay, we're going to switch to different training set. So each training set, we learn a different hypothesis with different prediction. We just average all of them. We take a square and take expectation outside. So the second term comes from here, just copy it down here. So it's just expectation of your learned hypothesis prediction on all kinds of training set, subtracted by the prediction made by the learned hypothesis from the current training set. If you take a closer look, this part actually corresponds to variance. This is a variance definition. Right? We have reviewed it in our, I think the second lecture or third lecture, whatever, right? But this is just the definition of the variance. So meaning that, okay, what is the variance of your prediction when you train your classifier at different training sets? And what about the first term? The first term, actually, we have discussed them a minute ago, right? First, f x star is constant to the data distribution D. And second, this expected prediction made by the hypothesis trained on different data set is still constant data distribution D, right? So that means it's not necessary to take the expectation again, because this square term has already been constant to the data distribution. That's our final decomposition results. You can see that the expected square error for our learned hypothesis in predicting particular test example x star can be decomposed as 2 terms. So the first term is the difference between the ground truth prediction and the expected prediction made by learned hypothesis across all possible training sets. We call this term as the bias term. And the second term regard the nature of our learning algorithm itself. Why? Because we just talk about the variance the learned hypothesis prediction. So if your learning algorithm is kind of sensitive to the data set, right? So you can imagine that the variance of the prediction made by the hypothesis trained from different data sets could vary a lot, could be big. So any questions so far related to the derivation of this decomposition? Is everyone comfortable with that? Or still, oh, this is just too simple for you guys. Okay, assume this is kind of like straightforward to everybody, right? But this decomposition, I'm assuming, although it seems straightforward, but does reflect some insights. So we can see that, okay, for any such kind of like square error, taking over all possible training set, this error actually reflects the property of the learning algorithm. So this error has two components. So one is bias, meaning that, okay, if I train our classifier on all kinds of training data set, on average, what is my difference? What is the difference between my prediction and the ground truth prediction? Right? This is the first bias term. A second term is that, okay, how stable my prediction across different training sets. So the more complex the model, you can imagine, because in every case, in every possible training data set, it can always well fit the training set, meaning that, okay, it can get closer to the ground truth prediction. So it has a small bias term. Meanwhile, it has large variance term. Why? Why it has a large variance term? Any thought? An idea? Yeah, we can consider decision tree, right? Just use decision tree as one case, right? Imagine that if we do not limit the growth of decision tree, we can just let it grow when all the training examples are well fitted, right? So now for one particular data set, okay, you grow the tree in that way. When it goes to be enough large, enough wide, it can perfectly fit all the training examples. Imagine now, just alter the labels for a few examples, or change the features for the examples. What will happen? To get a tree that perfect fit the change data set, it's very likely that your tree will grow in a totally different way. Right? That's very common, right? Because the more complex the model you have, the more likely you'll like fit the training data set very well. Then just a slight change of the training data will cause a dramatic change of the model structure, the parameter setting, whatever, right, to fit the new change of the data, although it's slight. So you can see, this is essentially a trade-off. So you have a complex, you have an expressive model, and then you have a small class. At the same time, because you're so sensitive to the change of training set, you have a large variance. And on the contrary, suppose you have a simple model, what will happen? An idea?
Variance will be low for that.
Mm-hmm.
What about the bias?
Can you speak a little louder? I didn't hear you.
So variance will be low, like as you explained before, that if we change a few samples, like change a few like sample values there, it will be a smaller, less complex model, would have smaller variance, but I'm confused about bias. What will happen to bias?
Yeah, that's a great question. Actually, once you reduce the variance, you actually enlarge the bias. Remember, we're training a simple model. Right? Training a simple model means that okay, every time it doesn't perfect fit to the training data well, right? So mean that okay, every time, well, as compared with decision tree or some deep neural nets, they get zero training error. I might only get like 70% or 80%, right? So on average, my prediction would still be further away from the ground truth. That will give you a large bias.
Okay.
Yeah, but benefit is that okay, because the learning algorithm or learning model is kind of so simple, right? It is much less sensitive to the change of training set, because if you change the training set, well, perhaps I just give the same model, which give a relatively similar fitting to the training set. So it doesn't have like motivation to vary a lot. So that's where we observe, like for simple models, it usually gives a large bias because it's inferior to fit to the training data, but as small variance, because a slight change of training data might not change the model itself.
Okay.
So now we can see that there's kind of a trade-off, right? For complex models, the benefit is that because it can fit training data so well as small biases, at the same time, it is not very stable to the change of training data, then it gives a large variance. For simple model, things kind of reversed, right? It gives a large bias, but small variance. So in practice, we're always trying to find a trade-off. We're not trying to use the most complex model, right? Might be like very small variance with high variance. We're not using most simple model, right? Simplest model, which may underestimate, underfit the training data too much, so that the bias is too large, although the variance is pretty small. We're trying to find a point where it can give this best trade-off. So now let us look at why bagging can help us with that. So we just use bagging decision trees to illustrate this. So as we know, like decision tree is a complex model. If you do not control its growth, right, it tends to overfit, so it has a small bias. But again, as we just discussed, right, if you just alter a few labels in the training set, the tree structure might alter dramatically, right, to well fit that change. So it has a lot of variance. And now, if I learn a bag of decision trees, right, each decision tree is kind of like lengthy, it's kind of wide, and it's complex. And when we do this average, what about the bias? The bias doesn't change, right? So imagine that you have a like random variable. You have a like n random variables, right? Suppose those random variables are independently and identically distributed, right? So if you take the average of those random variable, take expectation, it is exactly the same as you take the expectation of a single random variable, right?
Yeah.
So similar things happen here, right? If you just average the prediction from a set of strong classifiers, you won't change the bias because each of them are very close. Their average prediction is very close to the ground truth, right? If you take the average again, it's still very close to the ground truth. Then my question is, how about variance? Any thought? So the variance will be largely reduced, right? Because you take the variance of an average of a set of random variables. Right? In the best case, if all your random variables are independent, your variance will be reduced a lot. Right? So I want to probably, if I just write it down, it would be better, right? Can everybody see the whiteboard?
No.
Does it show up?
No.
Oh yeah, but by the way, any question regarding our discussion a minute ago? Okay, does this whiteboard show up?
No, nothing. It's a black screen.
Oh, come on. Let me do again. How about this time?
Yeah, we can see.
It shows up, right?
Yeah.
Okay, great. Seems like I have to do it twice. Okay, so to illustrate that, remember the bias term of the average of a set of strong classifiers doesn't change, right? But the change, what is changed most is the variance term. So suppose we have like H1, blah, 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 HT, right? So if you calculate the variance of an average of this T classifier's prediction. So I from 1 to big T and H I. So you can imagine because of this average, right? Because of this average. Because this average, your variance can be reduced dramatically. Right? So we can consider the oops, where is the pen? We can consider the extreme case, right? So suppose the prediction made by all the T classifiers are independent. Then what is variance of their average? An idea?
So this will be divided by T square, 1 upon T square summation of all the variances.
Yes, all right. Okay. So if H1 to HT are totally independent, right? So the variance of their average will be simply T. Oh, so I need to find the. Let me just use. Type something. So the variance will be 1 over T, such kind of things, right? Will simply be 1 over T times the variance of any output, right? So you can see if you use a single trait to make prediction, you get the you get the variance here, right? You get variance here. But if you use bagging, meaning that you average those T independent trees, you reduce the variance by 1 over T. Right? So imagine like you have like T equals 100, you have 100 independent trees. What happened is that, okay, your variance term will be reduced to 100 or 1% of previous of the previous variance. And then if we go back to Can you see the slide? Yeah. Yeah, if you go back to look at the variance term, it is largely reduced. And the bias term doesn't change. Then overall, the whole expected square error is largely reduced. That's why bagging can work. It doesn't change the bias, but by average a set of like less correlated predictions, we can significantly reduce the variance and in turn reduce the expected error. So someone may ask, right, what you're talking about is just about continuous prediction, like regression actually. How about the classification, like 0-1 error? And for 0-1 error, we do have a similar bias plus variance decomposition and works exactly the same way as we discussed here. That means when you use bagging, we can also keep the bias but reduce the variance to improve prediction accuracy. So any questions so far? So hopefully we can.
Will ADA boost also reduce the variance because that also does a kind of bagging, even though it's doing on weak classifiers? So will the theory behind ADA boost being a better algorithm will be the same as it will reduce the variance?
Well, that's a good point, but actually, when they show the generalization guarantees about ADA boost, they won't use the usually do not use the bias plus variance decomposition. The reason is that okay, yeah, they indeed decrease the variance, but at the same time they have a large bias, right? Because you use weak classifiers.
Yeah.
Then you have to show that okay, the whole trade-off globally gives a substantial reduction of the generalization error.
Okay.
Okay. And yeah, and in the next lecture, we're gonna quickly talk about random forest. We'll address another problem. Even the theory tells us, okay, bagging can improve by reducing the variance, but we see that you have to ensure that your different decision trees are kind of weakly correlated. If it's strongly correlated, it actually doesn't actually reduce the variances. We'll talk about how to increase the or decrease the correlations between different predictors, and that's the strategy we used in random forest. Okay, thanks everyone. I will see you on next Tuesday.
Professor,
Hi.
would it be possible to provide an extension for the homework, like 24 hours or something? That would definitely help.
Let me first count your request. So usually the things is like this. So if many students issue such kind of request, I would definitely consider for that. But if only like 1 or 2 or 3 to 5 students ask for that, this is hard to be approved because most of students they have take advantage of their time to finish them. I mean, submit it in time, and then if you request a delay, that won't be fair for other students.
Okay, that sounds good. Also, like for future homework, would it be possible to like make them do it by the end of the weekend rather than just Friday? Because most of the homeworks in other classes are due Friday for some reason. I don't know why.
Okay, that's fine. Yeah, I can definitely consider for that.
Yeah,
because the motivation for this is too, like I don't want to enforce you guys to work on weekends. That's the only reason. But if you people like to that. Like I said, deadline to be on Monday.
Yeah, I mean, if someone doesn't want to work on the weekend, that's totally fine. But other people could definitely use the time. Yeah, that's appreciated. Yeah,
Yeah,
thank
I
you.
definitely would like such an extension coming in the future, because just the entire crunch leading up till Friday, having the weekend if I need it, definitely makes things a lot less stressful overall.
Give you more flexibility, right?
Mhm.
Okay.
Maybe if it's possible for this homework, the TAs or maybe you could create a poll on what is it called, Piazza, and then the students can kind of vote if they need one or if they prefer one, and then we could let the decision, of course, be made by you in the end.
Okay, I can ask my TM to do that. But I won't do it today. I won't do it. I will do it like around the middle of, the noon tomorrow. I still want you guys to finish on time. Right? But if it is really too hard, and too many students are requesting like a delay, that's fine. I would definitely consider it. For that. But I do want everybody to work and say how good, how finally where you can get finally, because I need to evaluate. Okay, if this like 3 weeks time are enough for this work, for this amount of workload.
Cool. And I also have a question on the homework. It's more of a conceptual question. For the car problem where we only have categorical data, I get an accuracy of 100% on the training set at the maximum depth of depth equals 6. And I'm thinking that's the case because we have six kind of attributes to split over. So we're kind of completely splitting over everything at the end of the tree. Is that right?
Yeah.
And
you're
then,
talking about like a manual problem or coding problem?
for the coding problem,
You have a training error to be 0.
at only the maximum tree depth, at a depth of 6. At the other ones, at like 1 through 5, it kind of ramps up to that value.
How about the test error?
The test set is my best one is a little under 90, and my worst one is around 70% accurate at the max depth.
Okay, I will as normal.
Okay,
Yeah.
and I was wondering if that's normal. For the bank problem, I would expect if I'm using the same like applying tree method, and if I'm creating the decision tree in the exact same way, why wouldn't I get a training accuracy of 100% on that?
Oh, that's a good question. Actually, yeah, in theory, if you have enough features, you should be able to get 100% accuracy all the time. Imagine that in the worst case, like each leaf node contains 1 data point, right?
Mm-hmm.
But it's not always like that. For example, if you don't have enough features, like before you get to a purely labeled data set, you have used up all features. You have to stop there. You cannot get 100% training accuracy.
Okay.
Yeah, remember when we talk about ID3, we talk about the stopping cases, right?
Mm-hmm.
One stopping case is that, okay, if all the examples in the current node have the same label, we stop. We create leaf node, right? And the other case is that, okay, if my attribute set is empty, meaning I don't have any feature to do the further split, I have to stop as well.
Okay.
And the third case is like if my if when I grow a branch, right, grow a new branch, but unfortunately, the associated feature value, we don't have the corresponding examples. The corresponding examples are empty. It is possible as well, but But I don't think that will contribute to the non-zero training error.
Okay. So I guess from just to help me understand a little better, from the way I was thinking about it in my head, at a tree depth of 16, for the bank problem, when we have 16 different attributes, wouldn't it be the case where at that depth we have like the situation where we've created a leaf node for every single case that's possible in that training set?
Yeah. So the maximum depth of your tree is just 16, right? Because you only have 16 features.
Mm-hmm.
But what if, like, by going down level 16, you still have mixed labels in your training set, and then you have to stop. Like, you don't have choice because you don't have actual features to further split the data to get even purer. Like,
okay. Oh, I think I see what you're saying.
Yeah.
So if the final attribute, for example, is something called persons or people, and you can have values of like 2, 4, or more, then you have inside that like there's like 2 and 4, let's say, then it's not pure, but it's the final depth. So we can't be sure whether it will be one or the other.
you can't be sure. What do you mean by you can't be sure?
Like we have to use one of the stopping conditions instead of actually
Yeah.
giving it exactly what it's supposed to be.
Yeah. If you have used up all your features, no matter, I mean, whether the current set of examples are uniformly uniquely labeled, you have to stop.
Okay. And then
Yeah.
and my last question was, you mentioned that we would be building off of kind of our ID3 algorithm here, or our decision tree making algorithm for the next homework. And I was wondering if you would be able to provide like something to test our algorithm after the assignments due. Like if your implementation is correct, you should be getting this, or this is what this should approximately look like. There's some randomness to it if you implemented like a random choice at a tie of information gain, but just to get like a ballpark or something to do that, so that we don't compound our error from this assignment to the future assignment.
So actually, we won't like check the exact prediction accuracy you get. Only check, okay, if your training accuracy and test accuracy sound reasonable.
Okay.
And it won't like, for example, like you get like 97% training accuracy, while another, for example, your friend got like 100% accuracy. It will like your implementation is wrong.
Okay.
Just say, okay, whether your predicted accuracy, your training and test accuracy are in a reasonable range, and then we'll look at the logic flow in your code.
Okay, I think that makes sense.
Yeah.
All right, in that case, I guess I'll just cross my fingers and hope my code is working well. I think it is, or it's working approximately well. I just need to go through and make sure
You just need to go through and make sure your logic is correct, and testing with the data set and see if the results, I mean, the performance, all kind of stuff are consistent with what we have discussed in the past. But it's not, but we do not, but this is not like a, what kind of, I give you a calculation problem. You need to give me an exact number. It's not like that.
Okay. All right, awesome. I think that sounds good to me. It really helps.
Okay. That's great.
I had a question about the accuracies I was getting on the bank problem. Can I talk about that?
Yeah, sure.
So if I have the training file and the testing file as the same file, I see increases in accuracy as I increase the size of the tree.